Let us subject a pure capacitor. Capacitor has been denoted by capital C. Now you have a pure capacitor subjected to an alternating EMF. Then you see, imagine that a pure capacitor C has been subjected to an alternating EMF, and you are expected to calculate the value of current which is flowing in the circuit. You have to see the relation of this current, instantaneous current rather, with the instantaneous EMF which has been subjected to this particular circuit. Now see, again, if you involve the Kirchhoff's voltage law, then it says that the total potential drop around the loop is 0. So once you are jumping this EMF source, the gain of EMF will be taking place. This is EMF. But as you will be jumping the capacitor, then imagine that instantaneously, say, charge Q is there on the capacitor. Then this is Q by C, which is the potential drop taking place across this capacitor, and that will be made equal to 0. Isn't it? This is the Kirchhoff's voltage law you will be having. Now if you substitute the value of this instantaneous EMF, this will become equal to E naught sine omega t minus Q by C equals to 0. If you feel like, you can cross multiply. If you cross multiply, then Q becomes equals to C E naught sine omega t. This is the expression you are obtaining after cross multiplication. And now if your intention was to get the value of current, then naturally this current will be obtained if you differentiate this expression of charge, that is dq by dt. Remember that in case of integration we had to, in the case of inductor we had to integrate it, but in the case of capacitor we have to differentiate this expression. Now if you differentiate it, C and E naught, they are treated as constants, so that will be remaining as it is. This sine omega t differentiated will become cos omega t, and along with this cos omega t, this constant omega will also be coming outside, and it will be representing this way. If you try to further simplify it, it can be written as E naught upon 1 upon omega c. This is the modified way in which I have written it down, because there is some purpose involved into this. And cos omega t is being written as sine omega t plus 90 degree, because you know that sine 90 plus theta is cos theta. So sine omega t plus 90, that is written as cos omega t. This is the expression of I. You can compare it with I is equal to I naught sine omega t plus 90, where you can say that this I naught is essentially E naught upon 1 by omega c. What is the meaning of this? Meaning of this is that if you compare it with Ohm's law, which says that current is equal to EMF upon resistance, then here the term 1 by omega c is acting like a resistance offered by a capacitor. As you had omega L term for inductor, on the similar line you can see जो कैपेसिटर की रेजिस्टेंस ऑफर्ड है, दैट इज 1 by omega c. For that matter, in case you check the dimensions of 1 by omega c, that you will be finding equal to resistance. And so long as the comparison with EMF is concerned, you know that E is equal to E naught sine omega t. So this was taken as reference, isn't it? This was taken as reference. So with respect to this reference, if you compare the instantaneous current, you are seeing a term plus 90 here, that means the current is leading. So this current through the capacitor will be a leading current. This is our observation. So यहाँ पे दो चीजें जो आपने ऑब्जर्व की वो ये है कि what is the resistance offered by the capacitor to the alternating EMF, and what is the relation of phase lag lead with respect to EMF and current, and you are finding it is not lagging, rather the current is leading here. So the conclusions we got in the circuit of capacitors are as follows. The conclusions we are drawing here is that the resistance offered, again we will be calling this resistance as reactance. The reactance or resistance offered by capacitor the resistance or reactance offered by capacitor to an alternating EMF is 1 by omega C. You understand? जो reactance एक capacitor offer करता है to an alternating EMF, that has the magnitude 1 by omega C. Second important conclusion you are drawing is that the current through capacitor leads the EMF by 90 degree. You understand? Or pi by 2. In case the current is not leading by pi by 2, rather say 30 degree, 60 degree, that means capacitor is dominant. Capacitor के साथ और भी एलिमेंट सर्किट में हो सकती हैं, but capacitor will be dominant. But in case it is leading exactly by 90 degree, that means it's only the pure capacitor which is connected into the circuit. You understand? So if you try to plot these two conclusions graphically, then the graph will be coming out like this. The graphical representation of the entire situation here will be as follows. As you happen to do EMF being shown as reference, so this is EMF being shown as reference, and current through the capacitor is leading by 90 degree. That means यहाँ पे आप -90 डिग्री शो करेंगे. दिस इज द करंट थ्रू कैपेसिटर. आपने पहले जैसे देखा था कि जो लीडिंग करंट होती है उसको आप पहले ड्रॉ करते हैं. सिंस इट हैज बीन स्टार्टेड बाय 90 डिग्री, दैट मीन्स दिस ऑल्टरनेटिंग करंट इज लीडिंग द ईएमएफ बाय 90 डिग्री. सो दीज आर द कंक्लूजन्स you have drawn when you have subjected pure capacitor to an EMF source, then it is leading by 90 degree. Now all the three elements which you have subjected to an alternating EMF, in case you try to see all of them together, then we can represent it like this. There can be a vector way of representing everything in terms of, you can say, phase, then phasor representation of EMF, current through resistor, current through inductor, and current through capacitor. What we mean by phase is that on a general diagram you have to show their relative position. Remember that if EMF is being shown as reference, then EMF will be plotted on x-axis. If you remember that current through resistor was in phase with EMF, then current through resistor will also be plotted in this fashion. IR is current through resistor. Since this is in same phase, so both of them are following the same line. The current through inductor was lagging the EMF by 90 degrees, so it will be shown like this. IL. You understand? And current through capacitor was leading the EMF by 90 degrees. So current through capacitor will be shown this way. You understand? This is the phasor representation of EMF, current through resistor, current through capacitor, and current through inductor. But in case you try to show them in terms of their reactance, so that will be represented this way. Phasor representation of resistance R and reactance अगर इंडक्टर की रिएक्टेंस देखी जाए उसको हम X से इंडिकेट करते हैं, XL. X इज द सिंबल यू हैव यूज्ड फॉर रिएक्टेंस. अगर आपने सब्सक्रिप्ट इसमें L यूज किया है, दैट मीन्स इट इज फॉर इंडक्टर. इफ यू आर यूजिंग इट फॉर कैपेसिटर देन इट विल बी लाइक दिस. तो अगर आप इनको फेज वाइज रिप्रेजेंट करेंगे देन रिमेंबर दैट रेजिस्टेंस हमेशा यहां पे प्लॉट होगा. यू अंडरस्टैंड? जो इंडक्टर की रिएक्टेंस होती है उसकी वैल्यू आपने ओमेगा एल शो की थी, दैट विल बी फॉर्मिंग एन एंगल 90 डिग्री. यू अंडरस्टैंड? रेजिस्टेंस के साथ आप यहां पे देख सकते हैं एंगल 90 डिग्री फॉर्म किया है इसने. और जो कैपेसिटर के साथ बिहेवियर होगा, कैपेसिटर की रिएक्टेंस ऑफर जो होती है 1 बाय ओमेगा सी होती है एंड दिस एंगल इज हियर माइनस 90 डिग्री. सो दिस इज द वे you will be plotting reactance here, and the other diagram which you have shown, that is for current and EMF. Here also you can show the angle is 90 degree, the current through capacitor is leading by 90 degree. If you feel like, you can represent here by angle, this angle is 90 degree. तो जितनी भी बातें आपने लैंग्वेज में लिखी थी उनको अगर ग्राफिकली आप शो करते हैं in terms of their phase, so that is called phasor diagram, and phasor representation you have shown like this. Now in case you see it in terms of, say, the combination of all of them, then you remember that the idea is that they have to be treated like vectors. That will be essentially our discussion of the next session, but right now understand this is the way we have represented it in terms of phasor. तो वो एक वेक्टर की तरह भी यूज हो सकती हैं. एंड हमेशा हम जब क्वेश्चंस में डीलिंग करेंगे तो एट टाइम्स यू विल फाइंड दैट दी रेजिस्टर्स आर नॉट बीइंग ट्रीटेड एज स्केलर्स, रादर रेजिस्टेंस एंड रिएक्टेंस को हमने वेक्टर की तरह ट्रीट किया हुआ होगा, बट उनकी रिलेटिव ओरिएंटेशन इसी तरीके से होगी जैसे कि हमने यहां पे शो किया है. समटाइम्स वी मे आस्क यू टू रिप्रेजेंट द वेरिएशन ऑफ रिएक्टेंस of, say, inductor or capacitor with the frequency which is imposed on them, then how will you do that? Let us do that. Let us do the graphical variation of reactance of inductor or reactance of capacitor with omega. What is omega? Omega is the frequency of applied EMF you have. So this is a graphical variation of XL and XC with omega. So if you are trying it, then remember that on horizontal axis I have plotted omega, and on vertical axis I have plotted the reactance X. So long as the reactance of इंडक्टर इज कंसर्न, यू नो दैट एक्सएल इज ओमेगा एल. देयरफॉर जैसे जैसे ओमेगा की वैल्यू इंक्रीज करेगी द रिएक्टेंस ऑफ इंडक्टर विल बी इंक्रीजिंग लीनियरली एज इट हैज बीन शोन इन द डायग्राम. अंडरस्टैंड? जो आपकी रेफरेंस एक्सिस है उसके रिस्पेक्ट में आप देखेंगे कि जो इंडक्टर की रिएक्टेंस है वो लीनियर वेरिएशन के साथ इस तरीके से दिखाई जाएगी. एंड इफ यू सी द वेरिएशन ऑफ द रिएक्टेंस ऑफ कैपेसिटर, देन it has a rectangular hyperbolic shape this way. और उसकी वजह यह है कि यहां पे कैपेसिटर की रिएक्टेंस में 1 बाय ओमेगा का टर्म इन्वॉल्व रहता है. ओमेगा इज इन डिनोमिनेटर, सो एज द वैल्यू ऑफ ओमेगा विल बी इंक्रीजिंग, द वैल्यू ऑफ रिएक्टेंस ऑफ कैपेसिटर विल बी डिक्रीजिंग. सो this helps you, this graphical representation helps you in finding out that whenever you have to eliminate the high frequency signals, then you can subject it to an inductor, because for high frequency the inductor offers high reactance. But in case you want to eliminate the low frequency signals, then better subject it to a capacitor, because for low frequency capacitor offers larger reactance. You understand? So this is all in our today's discussion of alternating currents. Now before I go ahead, let me summarize what all we have discussed in our today's lecture. In today's lecture of alternating currents, first we discussed the advantage of AC over DC. We tried to see what is the meaning of average value of an AC, जिसमें हमने देखा कि ये 2I0 by pi की तरह हो सकता है. Same way we express the average value of an EMF. Then we discussed what is the meaning of RMS value or root mean square value of an AC. These were the ways in which you express the magnitude of an alternating current. Then to represent the direction of alternating current, we took help of the concept of phase lag or lead. Once we understood the concept of magnitude and phase lag lead or direction of alternating EMF, then we switched over to phasor representation of EMF current, resistance and reactance. Generally we preferred a separate diagram for resistance and reactance and a separate diagram for EMF and current. We had certain examples which demonstrated the concepts. You understand? So these are the things we discussed in our first lecture of alternating currents. Now in the next lecture we will be talking about various series and parallel circuits of alternating EMF, and we'll try to see what is the meaning of resonance of a series alternating current circuits. So this is all for today. Thank you.